and welcome to the first video on a series about topology. First, let's define what even is topology. Some of you may have heard this term before. Some of you may have heard even of the objects known as the Mobius strip or the Klein bottle, surfaces that intersect themselves. The Mobius strip has exactly one surface, despite it being in, it has one surface and one edge, so it's rather counterintuitive. Topology very much has to do with space and deformation, particularly continuous deformation, which will be given a precise definition later. We will define what it means to be a topological space, and we will define we will find a lot of different and often counterintuitive results with topology, some very interesting ones, as well as a variety of their applications. So the history of topology goes back actually to the 17th century, where Gottfried Leibniz, the mathematician and the philosopher, also known for inventing calculus at the same time as Newton, he had a vision of a certain kind of mathematics that had to do with only the places of where things are. Like, for example, if you had a bridge, then it would be concerned with the endpoints of the bridge and the fact that there's something connecting them. It's reducing a problem to its orientation in space. This was called the geometria situs and the analysis situs, of situs being like places, very much concerned with the orientation, the structure of space. And the very famous mathematician, the very prolific mathematician Euler, was once given a problem in, I believe, 1736, which had to do with graph theory. It laid the foundations for modern graph theory as we know it, where it had to do with, and you can look this up, the 7 bridges of Königsberg. If you could cross certain paths without without crossing your path more than once. He also found a very interesting formula known as the polyhedron formula, where the, otherwise known as the Euler characteristic, or the V minus E plus F equals 2 equation. So that really laid the foundations for topology, and it's sometimes said in math that things are named after the mathematician after Euler who discovered it, because he probably already did it. So let's start with the foundations, which have to do with set theory and mathematical logic, because those not only underlie topology, but just all of math in general. We'll use the approach known as naive set theory, as opposed to axiomatic set theory. Naive doesn't necessarily mean like not like aware, or doesn't mean like foolish. In this context, it just means that it doesn't necessarily follow as rigorous a set of laws or axioms as axiomatic set theory, which is more recently developed, does. Rather, it's more intuitive, and it's useful enough. It's more frequently used to start out with topology. So axiomatic set theory is its whole other course. It's a fascinating subject, but we'll use naive set theory for our purposes here. So we can think of sets, and you might have heard of this before. A set is more or less defined by its elements. A set is something that has elements, and it is defined uniquely by it. We'll use capital letters in terms of notation for sets, and we'll use lowercase letters for elements of these sets. And a word on terminology here, or rather notation again, if an element lowercase a is in the set uppercase A, we write membership like this. This is called a membership relation, with little a and this sort of epsilon symbol, big A. So A is in A. If it is not in the set big A, we simply draw this membership symbol, and then we draw a line through it to indicate negation. It's not in. Now, here's an important concept, that of set equality. This is that of logical equality or equivalence, where we're familiar with the equal sign, probably with numbers. We might write something like 1/2 is equal to 2/4, for example, because the equal sign shows that it's bridging two equivalent quantities. Similarly, if we write A is equal to B as sets, then A and B contain the exact same elements. There's nothing in A that's not in B, there's nothing in B that's not in A, and in fact they can be treated as the same set. An important observation, which we'll come to later actually after we define the subset operation, if every element of A is in B, then we write this over here, and that is to say A is a subset of B. So give me an element in A, and I can find it in B. If it's written like this, the closed end is towards the set that's contained, the open end is towards the container set. And the converse isn't necessarily true. Just by looking at this relation, you might be able to find an element in B that's not in A. You might not, but if you just write like this, that's all that's specified. And here's a very important note, which can be used to show when two sets are equal. If you want to show that this set uppercase A is equal to this set uppercase B, this is true if and only if, that's what this two-sided arrow means, if and only if A is a subset of B and B is a subset of A. We'll get to a concrete example later, but just think of it like if two things are contained in one another, how is that possible? They must be equal to each other as sets, right? If you give me an element in A, I can find it in B. You give me an element in B, I can find it in A. Since those are arbitrarily chosen, they have to be in agreement on all their elements, so to speak. Here's a certain case now. If A is a subset of B, but A is not necessarily equal to B, then we can write that A is a proper subset, and we just write it with this line below and a slash through it. It's strictly contained. Okay, so we've looked at basic equalities with sets and this if and only if relation. Now let's look at how to specify a set. And as I mentioned earlier, both in axiomatic and naive set theory, one defines a set by its elements. A set is no more or no less than the elements that it contains. For example, one can exhaustively list the elements of a set if you want to identify it. So let's say if big A is equal to these three ABC here, lowercase letters. We know that if B is equal to ABC as well, by like a transitive law, one can think of, then A is equal to B. So two sets are the same if and only if they contain the exact same elements. But this sort of runs into a problem if we have sets with a great deal of elements, right? If you had 100 or 100 million element, or even infinite sets, as we will see, there's no way that you can physically write it down. And of course, one might say, okay, for finite sets, it might take years and years and several stacks of printer paper, but when you come to infinite sets, which are very, very frequently used, it is literally impossible to exhaustively list them. So a very useful way of defining a set is by defining the property that all of its elements share. You define a set by a property. Here's an example. So B can be equal to the set of all x, we read it like this, of all x such that, and then on the right-hand side of this bar, you specify the property that it satisfies. X is an even integer. So some elements that might be in the set, we know that 2 is in B and 4 is in B because those are both even integers, but 17, an odd integer, is not contained in B. Okay, now we're going to get to operations on sets. And just the way we have operations on numbers, familiar ones like addition, multiplication, we can do things with sets to form new ones, right? We can form bigger sets or smaller sets, so on and so forth. So this is something called the union of a set. The union of two sets, A and B, is written like this with the sort of wider U symbol. A union B is equal to all x such that x is in A or x is in B. And this is the inclusive or, because in everyday English use, the word or can sometimes be ambiguous, whether you mean inclusive or exclusive or. But in math, this or is always going to be assumed to be inclusive. So this holds if x is in A and x is in B, for example. And let's look at that here. So let A be the set 1, 2, 3, 4, and then B 2, 3, 4, 5. What would their union be? Well, we want to find all the elements that are in A or that are in B, and they can be in both. And in fact, we find that 1, 2, 3, 4, definitely, all the elements in A. 2, 3, 4 right here, so there's no need to list them twice because they're already in A, and since the or is inclusive, we can write 2, 3, and 4 as in the union. And we have this 5 over here as well, which is in B, so it's in the union. So we have A union B equals 1, 2, 3, 4, 5. It's sort of like adjoining or concatenating sets, and repeated elements are treated as a single element in these unions. There is, in fact, a structure called a multiset, which permits multiplicities of elements, but sets treat elements as unique, and they only have single multiplicity. They only appear once. Here's another operation that sort of fiddles around with this or that we used here, this logical qualifier. What if we had and, right? So if we had all x in A such that x is in A and x is in B, that is, all of the elements that is contained in where the sets agree, with the overlap of these two sets, one can think, and there are nice geometric intuitions around this of like a Venn diagram and that sort of center where the two circles intersect. That's why it's called intersection. So A, and we write it with this upside down union symbol, this wider U flipped over, and it's the set of all x such that x is in A and x is in B, right? So if we have, going by our example earlier, the set A, 1, 2, 3, 4, and then B, 2, 3, 4, 5, we find the elements that they agree on, which is only 2, 3, and 4, because 1 is not contained in B, 5 is not contained in A. So 2, 3, and 4 is this intersection. And there's a special case. So in what we just saw, A and B do have elements in common, but it's very likely, for example, if we had B equals like 5, 6, 7, 8, that they share no elements. And in this case, the intersection is going to be empty. It has no elements, and A and B are disjoint sets. This begs the question of, what does it mean for a set to be empty in the first place? Well, a postulate of, or rather an axiom of set theory, posits that there exists an empty set. So a set with no elements, and this is different from a set containing 0, because 0 is an entity, and this is not to be conflated with a set with no elements at all. In this case, A and B are disjoint, and we write A intersection B equals, we write the circle with the line through it to be null set, or empty set. Another common notation for this is just two braces, where we specify like this in a set, except there's nothing between them, so it's just left brace, right brace. Here are some two useful questions, because we want to ask ourselves what are some of the properties of this empty set based on how we can relate it to other arbitrary sets. So we have A union empty set and A intersection the empty set. And let's think about this for a second. If union means all the elements that are in A or are in this one, it's sort of like adding by 0, because you're not gaining anything, but you're not losing anything, for sure. But you're also not gaining because there's nothing to add from the empty set. It contains no elements. Hence, for the answer for our first question, we have A union empty set equals A. You just get the same set when you take unions with empty set. Similarly, we want to ask ourselves, what is A intersection the empty set? And you might have guessed it by now. But if we're taking all elements in common between a set that has things and a set that has nothing at all, the only way for this to be, the only way we can write this is if A and the empty set are disjoint. More generally speaking, the empty set is disjoint to any given set. So A intersection null is the null set. So that answers our two questions. We want to look at a third operation which is frequently useful, called the difference of sets. It's like very much like subtraction in familiar number terms, but we just write it like A minus B to appeal to that, where it's the set of all x that is in A, but that is not in B. It's like if you have B and you're subtracting it from A, and then whatever you have left over is that difference of A minus B. So x cannot be in B, but x is in A, and it's written like this. Okay, now we're ready for some laws in set theory, where we take these operations of union, intersection, and difference, and we want to define some longer expressions or laws that we can use when we need to. And there are sort of two species of these laws that we will look at here. One of those is the distributive laws, and they behave very similarly to how multiplication distributes over addition. As you can see here, these two laws, A intersection B union C equals A intersection B union A intersection C. Take a moment if you need, because this might look like a lot at first, significantly more than what we've looked at with examples of union and intersection. But if you look a little more closely, you can see that union distributes over intersection the way that multiplication would distribute over addition, like so. Similarly, union actually does distribute over intersection, and so this is a very convenient secondary law that one can prove as well. I won't prove both of these, and I won't prove the next ones because they're extremely good exercises, but I will illustrate the proof of this first one to show what is the standard technique for showing that two sets are equal. Because as I mentioned, one way of showing that two sets are equal is by showing that if you have one contained in the other, and then containment the other way. So dual containment implies equality. So to do this, we show x and y are equal. It suffices to show just ISTS. X is a subset of y, y is a subset of x. Okay, so let x be an element in this left-hand side here. So we want to do this two ways because it's a if and only if statement, really. So we want to do the forward first, where if x is in this A intersection B union C, by this intersection being sort of and union being or, it sometimes helps to read this out like a logical sentence with qualifiers. So x is in A and x is in B or C. So x is in A and x is in B union C. I just did this in 2 steps. So it's written out here. And now there's 2 cases we can have given by this or over here. Either x is in B or x is in C we can look at. It could be in both, but those are covered by each case separately. So if x is in B, then x is in this intersection. X is in A, because we showed that here, and x is in B, because we're supposing that. So it's in their intersection. Then x is in this union A intersection C. And there's nothing special actually about this A intersect C. We could actually append anything here and it'll be true because it's automatically in this left-hand part over here. It's good to finish this for the case x equals C. It's totally symmetric, except instead of x in B here, you just write C, but it's good to think through why this is true. Now we want to show the converse because we've shown containment one way. That is, if x is in this left-hand side, then x is in the right-hand side. For this to be logically sound, we want to show that if x is in the right-hand side, then it's also in the left-hand side. So we take x is in this over here, this expression. X is in A and B, or x is in A and C. So if this is true by supposition, we just write this out like this. So x is in A intersection B, or x is in A intersection C. We once again split this in cases based on this or over here. Either it's either it's contained in this left-hand side or it's contained in the right-hand side. And it could be both, of course, like the last one, but those are covered by each. So if x is in A intersection B, we can write this as x is in A and x is in B. Right? So we know x is in A and x is in B, and now we know that x is in A and whatever else, because this doesn't really matter. All that matters is that since it's in B, it's in the union of any other set with B, hence it's in the union, it's in the intersection if it's in this and it's in this. Once again, you should finish the case where x is in A intersection C instead, and it's totally symmetric to the one we've covered here. Okay, so that's sort of the proof or a sketch of it for the first statement, and it's good to show the second one using a similar sort of technique. Then there's 2 more laws known as De Morgan's laws, which are very important, and they have to do with how unions and intersections interact with the difference operator. And they look somewhat complicated as well at first, but you can verbalize them as follows. For the first one, you can say, the complement of the union is the intersection of the complements. Similarly, for the second one, the complement of the intersection is the union of the complements, right? So if you have complements as sort of those outer things, then you just switch around union and intersection. And it makes a little bit of sense, especially if you draw this out diagrammatically, which I highly suggest, using Venn diagrams or something of the sort. So let's leave this as an exercise. Now we come to an operation, another axiom of axiomatic set theory if you want to think about it that way, but also a very useful concept known as the power set. And the power set is defined as A being a set, it's all x such that x is a subset of A. So the power set of A is the set of all its subsets. Let's take an example. If A is equal to this set ABC here, what is the power set of A? Well, automatically we know that for any set, you have the empty set contained in it, you have itself contained in it, because each element it agrees, and so it's a subset. And we can take A, B, and C on their own. So this null set, A, B, and C on their own. We can take A, B, C, and then we can take all possible groupings of two-element subsets. You have AB, AC, and BC, which is really 3 choose 2. So in total, you can count this out, you have 8 different sets. Better than exhaustively listing out all the elements of a power set to find out its cardinality or its size, there is a faster way if you know the cardinality of its base set, the original set A. Notice that if the cardinality of A is 3, the power set of A is 8, which is, not coincidentally, 2 cubed. The reason for this is a very, very slick combinatorial argument. If we want to find the number of subsets of a set, let's say A equals ABC here, we can go element by element and say, if we have a subset, for each element we can choose whether that element is in the subset or it is not. These are mutually exclusive, hence there's exactly 2 possibilities across every element. By taking 2 times 2 times 2 for each of the possibilities as independent events, we get that there's 2 to the third. So this is 2 cubed here. More generally, this can be seen to generalize as if the cardinality denoted by a hashtag of A is n, then the cardinality of the power set is 2 to the n. And this is very useful. We'll look at some interesting things with power sets later. There's a lot of fascinating results with infinities, actually, different kinds of infinities and countable versus uncountable ones. Really counterintuitive at first, but super fascinating. Okay, so we've covered these. Now let's look at arbitrary unions and intersections. We looked at unions and intersections of like small numbers of sets with maybe 2 or 3. But what if we have a lot more, right? Like a collection of sets, and we want to define operations across all of them. Then we take, let's say A prime is a collection of sets, and we want to define unions and intersections arbitrarily. So the union of across A is the set of all x such that there exists in A, that's this reverse E sort of looking thing, there exists at least one A where x is in A. And take a moment to absorb why this makes sense. Because you're going set by set, and if it's the inclusive OR operation. So if it's in at least one, then it's in the union. Likewise, intersection is defined as this. So it's across all A in this collection, where A is a set, where it's x, such that for all these sets A, x is contained in them. So x appears for every single set in that collection, because it's where they all agree, right? Finally, let's look at this way of defining new sets or larger sets called the Cartesian product. The Cartesian product is written with this multiplication sign here, and it's the set of all ordered pairs A comma B. And it's the set of all ordered pairs where A is in A, sort of the first coordinate, which is the first one written here, and little b in B, which is the second coordinate or factor. Sometimes this notation, parentheses A comma B, is ambiguous, because it can also be defined, as we'll see later, as the open interval. So when this is ambiguous, we'll write, instead of this ordered pair, we can write A times B, which is just equivalent to this. So we will look at some examples of that later on in topology, and that would be all for this first video. I hope you enjoyed it, and in the next video I'll be looking at functions and different kinds of functions on sets and subsets, and then we can proceed from there. Thank you.